Thank you for taking time to attend my presentation. And I want to correct, it's not a Siemens Foundation faculty fellow, it's a postdoc fellow. And today I'm going to give a talk which is entitled Solvated Electron from First Principles and Machine Learning. So I'm Jinggang Lan. I'm currently working as a postdoc at EPFL. So for those who are not so familiar with the solvated electron, first I would like to give you a brief introduction. What is solvated electron? So as you can see in the left figure, this is sodium dissolved in the liquid ammonium, so which is used for Birch reduction, belonging to the textbook for organic chemistry. The solvated electron can also dissolve in other solvents like water, methanol, and ethanol. So here you can see a typical cavity structure of the solvated electron. And solvated electron in water have been first discovered by Hart and Borg in 1962. And the solvated electron is known to be the smallest possible anion and also the simplest reduced agent. Understanding the property of a solvated electron can provide useful knowledge and fundamental implication for many areas like in electron chemistry, photon chemistry, and radioactive chemistry. Solvated electron have a wide range of applications. For example, it has been widely used for chemical reaction, such as Birch reduction, which can reduce the benzene molecule. And the solvated electron is also highly reactive, which can almost reduce all chemicals, such as CO2 molecule and nitrogen, and this can be used to produce formic acid and ammonia. And solvated electron is pre-circular white electron is also the primary intermediate that can cause DNA damage. And for example, when patients are taken X-ray scan, and solvated electron will generate in human body that can cause DNA damage. And solvated electron can be also used to activate some drugs, and that can potentially use as a treatment to cure the tumor. And in addition, many energy conversion processes also involve the participation of solvated electron, such as proton-electron couple transfer, and the solvated electron can form at the interface between the water and oxide upon the light excitation. And the solvated electron then can couple with the proton in the water and generate the hydrogen, which can be used for the energy conversion. For such a simple species, however, it involves complex physics and many of the questions and also many observations from the experiments having not been answered. And from the theoretical point of view, there are two main aspects to simulate the solvated electron. And the most knowledge is come from the so-called the one electron superpotential, like the TB model and the PWP model and LGS model. So those model where is based on a QMM formalism, the electron have been treated using quantum mechanics, and where the water or the solvent molecule are treated using empirical force field, like a simple point charge water model. As one can see, one can also use a more accurate many electron quantum chemistry method to simulate the solvated electron. And as one can see in this table, and many of these properties haven't been accurately predicted, and there are many phenomena have not been provided some insight. And in this part of talk, I'm going to focus on those questions where the one electron superpotential are not able to predict accurately, such as the diffusion and liberation dynamics of solid electron, and the interpretation of the Raman spectra, and also the temperature dependency of the absorption spectra, and whether this redshift of the absorption maximum is due to the thermal fluctuation or is due to the density change when the temperature increase. And in fact, to model this very simple species is a fully non-trivial computational task. The most used density function theory based on the generalized gradient approximation, and due to the lack of exact exchange suffer from the delocalization error, that lead to inaccurate description of the redox property and the bind alignment of a solid electron. So one needs to go beyond the standard DFT formalism to accurate model the solid electrons, such as using a hybrid functional or use a post-hydrophilic method like MP2 or GW method. And the hybrid functional is based on the different fraction of hydrophilic, and that's will make the ab initio functional not fully ab initio, which means it's still a little bit empirical. So far, the best in the market electron structure method to simulate solid electron is MP2 theory. So MP2 theory is known to give a good result for the liquid water and also the solid electron, which benchmark to the gold standard electron structure carbon cluster. MP2 is free of delocalization error, which is crucial to model the negative anion system accurately. And MP2 is also non-empirical. And this is a work have been done by my colleague Vladimir, and he carried out the first MP2-based molecular dynamics. And the system is rather small with only 47 water molecule plus one excess electron. However, this simulation is very expensive. And to run this simulation on one of the largest supercomputer designed, and it requires 20 minutes on a 250 hybrid node for each MD step. Basically, he only obtains 3 picoseconds and asks for over 1 million node hour. So this is highly expensive. And as we know, the nuclear quantum effects are not negligible when we want to accurate description of Aqueous system. And in the first part of my work, I will focus on the combination of a nuclear quantum effect and MP2 theory using machine learning method. So accurate physics is expensive and come with huge cost. And to combine MP2 with nuclear quantum effect by doing path integral molecular dynamics, in principle, is doable. However, the MP2 calculation is very expensive and is a few hundred times more expensive than standard DFT calculation. So our strategy is to apply machine learning methods. So we use a well-established Baylor-Pinello neural network where the energy and forces can be written as a set of 2-body and 3-body symmetry function. And the machine learning potential is based on our MP2 data, and then is able to reproduce MP2 quality with a much reduced cost. The overall workflow is the first, we recycle the dataset from previous MP2 based molecular dynamics and train the first version of a machine learning potential. And use the first version of machine learning potential, then we can run classical and quantum nuclei molecular dynamics. And since our initial dataset doesn't include the quantum nuclei phase space, we further select the representative configuration of quantum dynamics and recalculate those structures using MP2 level of theory. And then we can have a complete dataset that can handle both classical and quantum nuclei dynamics. So in the training, the solid electron is implicitly considered as a ghost particle. And that means there is no atomic representation for the solid electron. The solid electron is rather a structure effect for the water. And this turned out to be a good approximation since our simulation is based on Born-Oppenheimer approximation. And for a given atomic configuration of nuclei, there is only one electron structure correspond to it. So then we use a hybrid functional to visualize solid electron, and afterwards we can analyze and calculate the property of solid electron. And our machine learning potential is efficient and very accurate. So those calculations are carried out on a single processor, and every second we can get more than 10 energy and forces evaluation. So at beginning, the electron is fully delocalized, and then it will form a wet electron. And after about 1 picosecond, the electron will eventually localize to a cavity. So the localization timescale is about 1 picosecond. So this is in good agreement with experience observation. Since our simulations are rather cheap, we can run long time scale dynamics and that will enable us to understand the diffusion of solid electron. And the diffusion is initiated by the formation of the hydrogen bond between the cavity and its unbounded neighboring water. Here is the water B, and the water C will binding to the electron will replace by the other water, and then the binding water C will be slowly move outward to the solid electron. The diffusion coefficient of the solid electron are determined to be 0.28 for the classical nuclear simulation and 0.33 for the quantum dynamics. The inclusion of nuclear quantum effects improve the description of the diffusion constant by about 10%. And still, our simulation, there is still a gap between our simulation and experiment. That's might due to the MP2 overestimate the water-water interaction, and that make our liquid water ice-like. The inclusion of nuclear quantum effect reveal a new diffusion mechanism, is a transient diffusion of solid electron. And the transient diffusion mechanism is characterized by a twin cavity intermediate. So this diffusion mechanism is rather rare, and out of 50 individual molecular dynamics run, we only observe this transient diffusion happen a few times. And the electron can shuttle between two worlds and may eventually complete a diffusion step, as one can see in this video. So electron can actually jump from one to the other. And this mechanism have been only observed when we include the nuclear quantum effect. Here you can see a typical structure of solid electron, and the structure of solid electron is occupied by the excess electron involve 4 to 5 water molecule, having each OH moiety pointing to the center of the cavity. The average coordination number from our simulation is estimated to be 4.5, which is slightly lower than the estimation from a hybrid calculation. The nuclear quantum effect will broaden the first peak in both electron to hydrogen and the electron to oxygen due to the 0-point vibration motion, and will considerably reduce the long-range order, which is evident from the blurring of the second solvation shell. And to see the light into the Renaissance Raman spectroscopy, and we carry out the vibration density state analysis within the first water shell. And the experimental are marked in the dashed black line in the left figure, and the blue curve is a V dot of water, and the red curve is the 1/4 of the electron. So we plot the dashed line for the classical nuclear molecular dynamics and solid line for the quantum dynamics. As one can see in the figure A, the classical nuclei overestimate the bending mode for more than 50 wave number, and when we include nuclear quantum effect, the agreement is excellent. So there's only about our prediction predicts within 10 wave number close to the experiment. In the stretching motion, the agreement is less quantitative, and however, the redshift as induced by the presence of the electron is consistent with that observed in the experiment. And in the second part of work, I will focus on the temperature-dependent property of the solid electron. So within the one electricity potential scheme, and many work have attempts to understand the temperature dependency of absorption maximum upon the change of thermodynamic condition. And the non-cavity model, LGS, have been found to describe the temperature-dependent absorption maximum at fixed density in a quantitative correct fashion, apart from the slope is overestimated by a factor of 2. And the cavity forming model, TB, give a fair description of absorption spectrum, and the TB model reproduce the experimental temperature dependency of absorption maximum, but this agreement was demonstrated to arise from a density effect as the density of water decreased with the temperature. And this describes the experiment observation. And we use a very similar computational workflow that we train two machine learning potential, one for liquid water, another one for the solvated electron. So we run NPT ensemble using our machine learning potential, and then we convert to machine learning potential for solvated electron. And afterward, we cut a water cluster around solvated electron and calculate the absorption spectrum using TADD-FT with a QMM setup. That's the water close the solvated electron is treated using quantum mechanic, and the rest of water using a single point charge model, and the rest of the environment using a continuous solvation model. As you can see, here is the temperature dependent property of the liquid water. And the blue curve is the temperature dependent density of liquid water. As one can see, our machine learning potential predict pretty accurate temperature dependent property of liquid water. For example, the temperature dependent density is in good agreement with the experiment, this black line, from 300 to 400 K. And while the single point charge model failed to predict the density accurately at all those conditions. And with increasing temperature, the water becomes less order, which is evident in the RDF of oxygen, and only the first oxygen shell is visible when temperature is above 400 K. And next, we focus on the structure of solvated electron at different thermodynamic conditions. And at all temperature, the electron will localize to a cavity. And in the figure A and B, I plot the radial distribution function of the electron to the oxygen and to the hydrogen. And it's evident that vibrational motion globally broadens the feature of RDF. And this also contributes to the increase of gyration radius of solid electron, as one can see the red dots in figure D. And to see the light on the temperature dependence of absorption maximum, we carry out TDFT calculation, and the experimental curve are plotting the dashed red and dashed green line, and the same color in the figure A indicates the same thermodynamic condition as I mentioned previously. The TB model, as plotted in the green line, can capture the redshift of the absorption maximum. However, this is due to the temperature effect. The observed redshift is essentially due to the change of water density. And when the density are kept fixed, as one can see, this is a blue curve, so it remain constant. And LGS model is a temperature dependent and yield a redshift of 5.2 millieV, and this is overestimated by a factor of 2. And also the non-cavity model is essentially not correct. And our results show a redshift of 2.2 millieV, which in good agreement with experiment observation. And since the temperature and density change together in our simulation, and the origin of the redshift is not clear yet. So we further carry out two additional set of simulation. In the first set, we change the temperature by keeping the density fixed, as one can see these 3 points. And in the second set, we carry out the simulation at the same temperature by changing the density. As one can see, the absorption maximum is almost constant with a different density, only bearing a small redshift. However, the temperature have a more significant contribution to the Emax. And to understand the reason why, we consider a one-dimensional square well model with a finite barrier. The vertical bending energy is defined by the energy level of the ground state to the vacuum. So the delta E, the excitation energy is calculated by from the ground state and the first excited state. So by solving this model using Schrodinger equation, and basically we can get the curve as plotted in the pink in the figure A. And basically we can conclude from our result that gyration radius is a key factor that causes temperature dependence of absorption maximum. And to the end, I would like to summarize my talk. So we combine accurate electron structure theory and machine learning that allows for the quantum dynamics of solid electron, and nuclear quantum effects improve the description of a solid electron for the static and dynamic property. And the quantum effect enable a previous unknown diffusion mechanism haven't been seen in the classical molecular dynamics, which involve a twin cavity. And the temperature dependence of absorption maxima is due to the temperature dependent gyration radius rather than the density of the water. And the take-home message is the quartz particle, like a polaron, exciton, can also be simulated using the machine learning method. And to the end, I would like to thank my PhD supervisor and collaborator, and also my current collaborator Alfredo. And the first part of work have been collaborated with Venkat and Michele, and this work have been funded by SNF and LabCheck, Marvel, and the computing resource from the CSCS. And also thank you for attention.